Yes, sir, we can hear.
All right, so this is the second part of the chapter two. It's about biochemistry. Now, we mentioned yesterday or earlier that anything that contains carbon refers to organic material or compounds. All right, so usually a lot of bonds are forming between the carbon because on the outer shell electron of the carbon, there were only 4 electrons on the outer shell. Okay, so that way, that gives the ability for a carbon to be able to bind covalently and share their electron with the other elements. Inorganic compound, they do not have any carbon. Water, salt, many acid and bases, there are examples of inorganic compound. All right. We discussed some of the properties of water in an earlier lecture. High heat of capacity. It can absorb and release large amount of heat. This is kind of like redundant. Heat of vaporization. It's a great solvent. So all of those things we discussed already, and that gives it a great solvent for many different reactions to take place. We also mentioned the reactivity and the cushioning. Uh, a lot of water is around our organs, giving our organs, cushioning capability and such. All right, so I think that's where pretty much we left off. Now I want to talk a little bit about acid and bases. All right, so again, we're looking at a little bit of chemistry. Anytime you're releasing hydrogen ion, all right, or also known as a proton, because hydrogen ion, it doesn't have any electron. Remember, the hydrogen had only 1 electron. So when you donate that, what will happen? The electron is gone. Now it becomes hydrogen plus. All right. So the plus is because it has an extra proton. So sometimes this is called a proton. All right. So when we say proton donors, what that means, if it combines with something else, at least it has the protons. It doesn't have the electron, but it has the protons. All right. So in here you have the chloride anion. Remember when we say anions are negatively charged and cations are positively charged. All right. So this negative and positive, they can combine with one another and make up the HCl. Or in this case, hydrochloric acid can actually dissociate to hydrogen ion or proton and chloride ion. But this is the proton. The more proton you will have, the higher the acidity will be. All right. So if something has a very, very acidic, like for example, the stomach has a lot of hydrochloric acid in it. Uh, there is certain type of cells known as parietal cells in the lining of the stomach, all right, that produces hydrochloric acid, parietal. Parietal cells, they produce hydrochloric acid, all right, in the stomach. So stomach is very acidic, all right. What does that mean? What does that mean? If you remember in the stomach, there were like, larger cell and there were like chief cells that were like a smaller and they produce hydrochloric acid. And these were the uh, parietal cells. All right. Anyways, the point is that the stomach becomes really acidic. Of course, this happens for a reason. So you could break down the protein as well as some of the microbes that enter our digestive system. We will look at the role a little bit later, but there is a connection when we're talking about acids and bases and things like that. All right. Now, bases actually offer hydroxyl ion. They are proton acceptors. So they can accept the proton. These are proton donor. Acids are proton donor. These are proton acceptors. So NaOH, for example, again, it can dissociate to the sodium cation and the hydroxyl ion basically. And this hydroxyl ion, the more hydroxyl ion you will have, the higher the basicity will be. Now, what if you have equal number? This one is proton acceptor, this one is proton donor. As you can see, you get H2O. So hydrogen plus hydroxyl ion, that will give you the H2O. All right. So when we say water is neutral because the number of hydroxyl ion is the same as the number or concentration of hydrogen or protons. All right. So if they are the same, they're not acid, they're not base, they're equally number. All right. So if you have something basic and you give it hydrogen ion, then it becomes neutral. Vice versa, if you have something acidic and you give it some hydroxyl ion, then you're making things neutral. All right. Interestingly enough, sometimes when a stomach is really, really acidic, because maybe having too many spicy food or for whatever reason, the stomach is irritated because, a person, let's say, drinking a lot of alcohol, coffee, Coke, 7 Up, they're all very acidic, spicy food, grapefruit juice, all kinds of things and so on. The stomach, in addition of that, producing hydrochloric acid, which again, due to the negative feedback, it should produce less. But either way, when the stomach becomes really acidic, all right, now you're getting a lot of these basically. All right. So a lot of times individuals might take antacid. Antacid. All right. You probably heard about Tagamen HB, Rolaids, a lot of products out there that you can take for Tums. All right. You might have heard about those products. Those are antacid. All right. So what will happen then? Well, when you take the antacid, stomach has a lot of hydrogen ion. When you're taking antacid, you're trying to neutralize that so it won't irritate your stomach. All right. Of course, you should not be taking it so much. All right. This is just should be a temporary relief. Otherwise, our body doesn't do very well when, you're trying to uh, neutralize acidic condition. Now you might say, why? Right? Why not? Well, uh, it's a lot of times when you're eating something, this acidic condition break down and eliminate bacteria. All right, you might have heard about that. Oh, we are in the verge of COVID-19, but if your food is contaminated, let's say has viruses in it, many scientists believe that that's not going to do anything. Why? Because it goes into your GI tract. Why? Because it goes into your stomach, and the stomach is going to kill pretty much the bacteria and viruses and all that. But when you neutralize things, that gives opportunity to a lot of bacteria to flourish now. All right, which a little bit later on, they're going to go to the small intestine. After that, is going to go to the large intestine and so on. So a lot of bad bacteria might actually occupy your intestine, cause diarrheas and other things as well. All right, so think about that for a moment. All right, I'm trying to give you guys a connection to this. A lot of times, people just see hydrogen ion, chloride ion. Oh my God, it's chemistry. I don't understand it, and things like that. No, everything is related to one another. I told you this earlier. There is an interrelationship among things. All right. And this is another interrelationship. One of the things that a student usually find it useful is to find the connection between them. All right. And understand the concept. All right. How is it implemented? There are so many different applications. But once you get the foundation of it, then you have to implement that. All right. Think about another scenario that might involve acid and base. Think about these things. This will be actual learning. This would help you, all right, to remember it for many, many years to come. Not just memorizing, oh, okay, when these two are the same, then it's water. It doesn't give you anything, all right? So let's go ahead and take a look at the pH scale. Uh, as the pH scale, you could see pH scale neutral is pH is 7. All right. As the pH reducing, you could see the number 6, 5, 4. You know, the pH is getting lower, the acidity becomes higher. So this is more acidic. The pH is getting more, or the number getting higher, the maximum is 14, then basicity increases, more basic. Okay, so neutral is 7. All right, now when we say you know you can look at some of the examples. All right, blood is actually about 7.4. All right, so it's kind of like neutral almost. All right, urine is 5 to 8. Most of the time, the urine is around 6, all right, which is telling you it's a little bit acidic because, again, extra acid. Here's when your blood is too much acidic. Now, sometimes it can happen, you get a condition known as acidosis. But if your acid is increasing because you're drinking alcohol, you have some acidic food and so on, eventually it's going to go to the kidney. This is the renal artery, for example. And if you recall, again, going back to the anatomy, all right, uh, there was a ureter and the waste and so on, and extra acid can come out of here on the ureter. The ureter is linked to the urinary bladder, and the urinary bladder is linked to the urethra. So what you're dumping is excess hydrogen ion. All right. So what happens? We started with high acidity. As the acid or hydrogen ion removes, now you're lowering it. Again, negative feedback system. You see, this is another example. All right. Uh, always, it's a good idea not just to read the material and try to memorize everything. For everything that I tell you, pause, think about a scenario, think about, like, what is happening, what can you think of, like, in our sense, physiology that might be related to this concept. And that would help you understand the depth and the complexity, and making things a lot easier for yourself. All right. If you're thinking about how you could involve what you learn, all right, is a lot better than just like memorizing things. All right. So, anyways, they go based on logarithmic scale. So, what that means, when we say 6, that's 10 times more acidic than 7. When you get 5, that means it's 100 times, 10 times 10, 100 times more acidic than 7, and so on. So when you get to the 4, grape tomato juice in this case, it's 10 times 10 times 10, or 1,000 times more acidic than the water. So again, they go based on the logarithmic scale. Our body, interestingly enough, it actually can deal with the acid a lot better than the base. I'm not going to get into a detail with it. However, our body does a lot better dealing with the acid. All right. Now, let's say this is hypothetical. Let's say you find yourself in the room, all right, and chain up to the chair, make it dramatic to make it exciting. All right. You saw some movies like that. They wake up, they don't know what happened, and they're chained up, and there is a task. I think there was a movie called Saw. It was a really sick movie too. But anyways, uh, I did not like it. But anyway, let's say that you're getting up, and there is two. One, it says, is an oven cleaner. Oven cleaner is very basic. The other one, let's say, is something with high acidic in it, like maybe sulfuric acid or something like that. All right, very acidic. And they tell you in order for you to get free and the chain would come off is by drinking one of these. Which one will you choose? Well, knowing the physiology of the body, yes, acidic material sounds scary and everything, and the acid is going to mess up all the lining and epithelial is going to get really messed up. And as you're drinking it, probably is going to damage your esophagus and so on. All of that is true. Your blood is going to get acidic, but we can deal with it a lot better than oven cleaner. Okay, uh, high high hydroxyl ion can actually kill you. All right, so yeah, pick this one if you have to. All right. What are buffers then? Well, yes, the kidney is working, and I just told you you could dump some of the acids using the kidneys and so on. But we also have a beautiful system. Buffer resists the change in pH. What that means that it does not allow the pH to dramatically change. Okay, let's say that you have water. Water is neutral, right? So if you put in like, something that is acidic, like let's say a little bit of acidic hydrochloric acid, the pH is no longer going to be 7. All of a sudden, from 7 is going, that was water, we started, is going to go maybe to pH 3. That's a drastic change. All right, that's a very drastic change. However, you might have a buffer. Bicarbonate is a buffer, and you have water and bicarbonate in here, okay? And now you put in the hydrochloric acid. It started off with 7, but now after putting the same amount of hydrochloric acid as you put it in this one, all right, it might be like 6.5. So it's resisting the change in pH. It's not dramatically changing. All right. And that's a beautiful system to have. And a little bit later on, I promise to talk a little bit more about this. But basically, uh, the formula, there is a formula we're going to get into a little bit later on in the respiratory system. And the formula is carbon dioxide plus water. All right. It gives you, when I do this, that means it can go both ways. It gives you H2CO3, which is carbonic acid. And this becomes also hydrogen ion plus HCO3 negative. And as you can see, this is our bicarbonate. You'll see the application a little bit later on. But because I'm using both arrow going this way, what does that mean? That means I can go this way too. So a lot of times when you have this in your system, say for example, in your blood, here's the blood, all right? And here is the bicarbonate, all right? Let's say you ingest something that is acidic. Yes, earlier I told you the kidney is going to dump some of the acid, but sometimes you don't need to put in so much work for the kidney because when you are absorbing hydrogen ion, let's say through whatever it is, alcohol, something is spicy, vinegar, all that stuff, all right, it adds to that. So guess what? Now you're making a carbonic acid. Now you're making a water and carbon dioxide. Carbon dioxide we can expel. Water remain. So guess what? We just neutralized it. You see how the important the bicarbonate is? All right. So the bicarbonate can be really useful at times to achieve equilibrium. And that's what we're doing, homeostasis. All right. That way your blood is not going to drastically change like this one. All right. His blood, maybe a little bit gets acidic. But can you keep drinking and taking up acids and so on? No. Eventually, you're not going to have enough bicarbonate to deal with all this hydrogen ion. All right. If your maximum has reached, now a little bit of hydrogen ion, boom, is going to make the blood very, very acidic. And when that happens, a lot of proteins they start denaturing or perhaps changing their shape. A lot of enzymes are not going to work, so a lot of bad things can happen, folks. All right, moving right along. Uh, let's go ahead and take a look at some of the organic compounds. So there are four macromolecules. They are all, organic, contains carbon, carbohydrate, lipids, protein, and nucleic acid. All right, the first one is the carbohydrates. Another name for carbohydrates is called what? Polysaccharides. Poly means many, saccharides means sugar. Carbohydrates, a good example of it would be starch, glycogen, things in that nature. And then again, if you break down these carbohydrates, we get simple sugar. Simple sugars such as glucose, such as galactose, such as fructose, such as, there's a lot of ribose, there's a lot of different sugar. All right. Next one is the lipid. For our sense, there are different type of lipids, phospholipid bilayer, the glycolipids, there's different type of lipids. Steroid hormones are lipids, triglycerol is a lipid. We'll discuss some of those as well. And then we have protein. Proteins are chain of amino acids. They're made out of amino acids. So if you break it down, you get amino acids. All right. And nucleic acids is basically pretend that this is DNA and RNA. These are our genetic material, and that can break down into, nucleotides. Nucleotides. And the lipid, most of the time, triglycerol, which again breaks down into free fatty acid and glycerol molecule. All right. So basically, this is a way to break things down. Can you go the other way? Absolutely. Can you make things when you have them? Yes, we can. In other words, you could go from here to here. 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 But obviously, you have to have many amino acids to put them together to make the protein. You have to have many sugars to put them together to get polysaccharides. So this you have to have monosaccharides, you get polysaccharides. Right. So yes, remember what we start off is called the reactant. What we end up is product. So let's go ahead and take a look at the carbohydrate close up. Here are different examples of the sugar. No, you don't need to memorize all these shapes and forms and so on. They have a lot of carbons, they have a lot of hydrogens, and so on, but they are one single unit. So they have a weird geometric shape. Most of them are pentagon and hexagon shape and a ring-like structures, as you can see. But that's not really important. When you get organic chemistry, you will learn about this more detail. Going forward, you can see these are the disaccharide. Disaccharide means two sugar. So you have the glucose and you have the fructose. They are combining with one another and you're getting the disaccharides. In this case, the disaccharides meaning two sugar together, and that's what it is. All right. But how is that achieved? How is it that we get the disaccharides? The disaccharides, we get it by losing of the water. Notice that the water, H2O, in this case, one hydroxide from one molecule and another hydrogen from another molecule, that is making up the water molecule. So if the water molecules is being lost, all right, these two join with one another. So this is your A, this is your B, A plus B, you get the AB. And the AB is now joined together and now you're making a bigger molecule. All right. So anyways, what about when we wanted to make? Now, because the water is being lost, this is also known as dehydration. When you're dehydrated, water is lost. All right. Now, what if you wanted to break things? In other words, you have the AB, you want to go to the A plus B. Pattern of reaction is something that we discussed in a previous lecture. So again, we discussed about combination and decomposition reaction. So what I just explained was the combination reaction. What about decomposition reaction? Water can come in and break these bonds, all right? And as a result of that, we can get to a smaller molecule. And this is called hydrolysis. Hydro means water, lyse means break. Okay, so there is a chemistry involved, and but for our purpose, you want to know when you could do hydrolysis, breaking. A lot of breaking means also catabolic reaction, means like when you are having a bigger molecules, you are separating it into a smaller one. All right, so there are many different examples of the disaccharides. What if you continuously putting more and more sugar together? What do we do after that? Well, if that happens, then you could make many sugar polysaccharides. Glycogen is a form of a polysaccharide. I told you a lot of times sugar is being removed from our blood and is stored into our liver in a form of glycogen for energy supply. All right. So we discuss about the role of insulin and glucagon. All right. If you haven't looked at that lecture, you could look that up again. But this is polysaccharide, so there's a lot of energy in these bonds. You need the energy. These bonds needs to break. These bonds needs to break. All of these breaking and so on requires energy, but then it releases some energy that you could do work. That's why sugar is kind of like uh, you know basically the sugar is kind of like all right. So that's what happens as far as the polysaccharide goes. So before we go to the lipids, another important concept, when you are eating something, you breaking things down. So the sugar, it breaks down. you know when you're eating the bread, has polysaccharides. When you're eating potatoes, has polysaccharide. When you're eating banana, has polysaccharides. These polysaccharides, you need to break it down, so our body, our digestive system breaks things down. You get energy from it. But now you have a lot of sugar, all right, and you may not need that sugar. So here's the blood vessel. You have high glucose, for example, and guess what? We wanted to lower it. On the other hand, we also want to reserve it for later. We don't want to get it to waste, all right? Sometimes, yes, eventually can go to the kidneys. Kidney can get rid of the glucose too, all right? But these are valuable for our body. So what happens? The insulin comes in and you remove that, put it in the liver, we discussed, and you get lower glucose. And that was a negative feedback we discussed, and achieving homeostasis, all right? So everything is so beautiful when you look at the concept that is going on, all right? So let's go ahead and take a look at the lipids. Again, neutral fat or triglycerol is what we're going to put our emphasis in it, but part of our membrane, cell membrane, phospholipid. Also, a lot of steroid. You probably learn about a lot of these steroids, or at least about testosterone, estrogen, progesterone, aldosterone, cortisone. There are a lot of different steroids, hormone, and they all do a lot of different things, whether it's a sexual behavior or whether it's a muscle mass, development of breast, all that's secondary and sex characteristics in male and female. So they have a lot of different role, not to mention the growth and development of the reproductive organs require this steroid hormone too. So let's go ahead and take a look at the concept. Remember, two important concept in here is you want to break things and you want to make things, all right, for a reason, all right? Breaking things, hydrolysis. Lyse means break, hydro means water, okay? Making things, dehydration. You're making a larger molecule. All right, so here you have a glycerol. Here you have three fatty acid, and again, highlighted water. Three water in this case are being departed. It's lost. Hydrolysis. I'm sorry, not hydrolysis, dehydration. And as a result of that, you're making triglycerol. All right. This triglycerol, because it's really fatty, is not a good thing to have so many of them, because they could reside in our blood vessels, clog up the arteries and things in that nature. So again, your blood triglycerol level indication whether you have a healthy diet or a bad diet. It turns out that a lot of times, we have a lot of bad diet, Kentucky Fried Chicken, Popeyes. Somebody says they like to eat in Popeyes, you know, uh, A lot of you actually surprisingly say you like to eat at home. That's great. I like to eat at home too, especially nowadays with the COVID-19. You just don't want it to go sit out and then things in that nature. But now I know all the good places to go after, if we ever get lifted from, staying home and all that. Right. But, anyways, no, I just wanted to find out what are your interests. Uh, Personally, I like all kinds of food. I was surprised so many people like Chinese food and Thai food and Japanese food and such. Usually, I hear, you know, uh, I used to hear a lot of hamburger, steak, things like that. But now it's a lot of Chinese food and Asian foods and things like that. I like all kinds of food, to be honest with you. Uh, Spanish food I really like. Something that is spicy I really like as well. So if it's Chinese food, I like it spicy. Anyways, it was really interesting. Uh, Thanks for that, Pop. All right, so lipids can also be part of our membrane. Again, going back to the anatomy, double layer surrounding our cell is called phospholipid bilayer. All right, but the construction of it, if you look at one of those, you'll see that there is a polar region and there are non-polar region. The non-polar region usually it says is a tail, and the polar region it says is the head region. All right. Why is it called polar? I mean, take a look at electronegativity, phosphate, oxygen, the negative. All right. All of those are electronegative elements. So they are unequal distribution, making here polar versus the carbon and hydrogen, a lot of them, this is making it non-polar. All right. So it turns out that the head is polar end, and we also known as phospho uh, uh, it turns out that it's called hydrophilic, and the tail part is known as hydrophobic. They don't like the water. All right. All right. So this is important because you don't want just anything to go in and out. You want things to be regulated. And one of the things that goes in and out is oxygen and carbon dioxide. So when they go in and out is because they are also nonpolar. Now, this molecule is both, has polar and nonpolar, but take a look at the nonpolar region is actually a lot more. And when you're looking at the cell, it has, let's put it this way, it has, polar again, head and non-polar. So maybe I need to show you in a different slide. So we're looking at the cell, and this is the double layer. And right over here, you see the polar heads. And if you go ahead and take a look at, it looks something like that and something like that. All right. Interestingly enough, look at the non-polar region is a lot. And the polar region is always facing the water. This side water, this side water. Outside of the cell is water. Inside of the cell is a lot of water. So that's why it's called hydrophilic, means water loving. The head region likes the water. That's why they're facing the water. Hydrophobic, like arachnophobic, people are scared of a spider. They don't like the water. They stay in the middle. Huh? Okay, so that takes care of that. But other than that, there are other type of fat as well, or we should say lipids, and that is Steroids. A lot of hormones are a steroid. Cholesterol is a steroid as well. Many of the hormones, their base is the cholesterol. That's their derivative. Okay, they have a really uh, unique shape that are many ring structured together. In this case, there are four of them. They have very, very small polar region, but the majority of the region again is non-polar. All right, so neutral fat, phospholipids, a steroid, fat soluble vitamin, lipoprotein, they're all unique. And again, the examples of it we discuss. Uh, you could find these vitamins A, D, E, and K. They are fat soluble vitamins, so you have to be careful of taking it. You cannot keep taking it forever. And the lipoprotein is also is important because they can help in transport the fatty material in the bloodstream so they don't get clogged up. There is a HDL, high density lipoprotein, and there is a LDL, low density lipoprotein. And these are the bad ones, and this is the good ones. Maybe in the digestive system, we get the time, we can talk about it. But right now, we have a lot more to cover. All right. So the amino acids is a building block for making protein. As an analogy, I would like to think of amino acids as Lego pieces. When you put in the Lego pieces together, you can make something larger. And the way that the Legos are, everyone is a unique structure, but they fit one another. In other words, they have a structure that goes into another structure, like a male part and the female part, and they combine with one another. This is really similar in amino acids as well. When you're looking at the amino acids, they have two parts. You could think of it as a male and female part, or carboxyl group and a amino group. All right. So one is a nitrogen group, another one is a carboxyl, carbon and oxygen and uh, hydroxyl group. So all the amino acids, they are similar in structure with the exception of one region. So look at this. For example, this is the acid or carboxyl group. This is the amino or nitrogen group. All right. And these are different amino acids. You could see this is called glycine. This is called aspartic acid, but it's the same thing. They all have these two groups that they are actually connected to the carbon. But what is different between these two is this region right here, showing you in green. This is called the variable group or R group. R means is variable. It's different from one amino acid to another. We have about 20 amino acids, so there are different only in the R region, not the other areas. So what happened is these two parts, they connect with one another. These two parts connect with one another, okay? So they form a covalent bonds, but because we wanted to indicate that it's, you know, it happens in the amino acids, it's kind of like this is one Lego, this is another, they fit in one another. So a lot of times this is also known as a peptide bond. So on the next picture, you could see how it's forming. Dehydration again. Water is lost. These two, call this A, call this B. Now I call this AB. And the covalent bonds between them is called a peptide bond. Why? Because another name for protein is called polypeptide. So peptide bond is because you can make a lot of it. And this could continue. So this one can, uh, hook with another amino acid and so on. What if you want to break it? Hydrolysis, same idea. Lyse with water, break with water, and you get two amino acids. Remember, you could take out the Lego pieces, you could join them together. All right. If you want to make them bigger, some objects, house, buildings, etc., you join them. That would be, you know, uh, keep adding it and so on, which you're making a polypeptide, which is another name for it is a protein. Protein is basically combination of different amino acids, and there are 20 of them. So imagine that there is only 20 different Lego pieces, some shorter, some larger, and different shapes, and because of the R group, and that's how it is. A structural level of proteins are as follows: primary, secondary, tertiary, and quaternary. Primary structure is only peptide bonds, only peptide bonds. So it's a linear structure. Secondary structure is peptide bonds plus hydrogen bond. All right, and tertiary structure is peptide bonds plus hydrogen bonds plus other bonds. This could be disulfide bonds. This could be other interaction, etc. Okay, so it gives it a three-dimensional structure, and when you have many, and this making one subunit. When you have many subunits, you get the quaternary structure, two or more subunits. All right. So again, if we go ahead and take a look at the structure, this is the primary or linear. So think of it as this is one amino acid, this is another amino acid, this is another amino acids, etc. But some of the amino acids, they could have a hydrogen bond pair too. So think about these three dots as hydrogen bonds, and these three dots as hydrogen bonds. All right. And the way it works is amino acids, they could actually kind of like a sheet like a structure because of the hydrogen bonds that I'm showing you in three dots. They could actually have attraction going on. Remember, hydrogen is involved, a slightly negative, a slightly positive, and so on. So they could act like, like a linear, I'm sorry, like a sheet of fabrics on top of one another, for example, all right, connected together by hydrogen bonds as well as a peptide bond. So these are hydrogen bonds and these are peptide bonds. So it has both. Alpha helix is another secondary structure. So these are kind of like twisted like this. So again, you could have, these are amino acids, but you could have, hydrogen bonds as well. Okay, so again, you can Google it to see the three-dimensional structures. This is just ball and stick kind of form, but there are many different ways of showing it. Tertiary structure is all of those together, plus other type of bonds. You might have disulfide bonds, attraction, slightly negative, slightly positive. They attract one another. Polar group, they attract one another. Non-polar group, they attract non-polar group, etc. So it gives it a unique three-dimensional structure, and this is called one subunit. And quaternary structure when you have two or more. In this case, this is an example of hemoglobin molecule, which consists of 4 subunits. All right, this is important because of the fact that they can carry oxygen, O2. All right, O2, O2. Each of these hemoglobin can carry 4 oxygen molecule, and this hemoglobin happen to be, we call it HB. A lot of them are actually in our red blood cells. They are having a lot of concentration of hemoglobin so that they could transport gases. They can also carry the carbon dioxide too, all right? So is extremely important to have the correct structure. If you do not have a correct structure, they may not be able to do their job. Like earlier, the sickle cell anemia that we discussed, they are sickle, so they cannot go ahead and efficiently transport. Okay. So if the protein is malfunction, most likely is due to the alteration in the shape. All right. And there is a lot that goes with it. All right. But we can go ahead and take a look at this shortly. So let me go ahead and pause at the moment. So we were talking about the structures. These are two different type of proteins. Sometimes the proteins could be like a rope-shaped structure, all right? If it's rope-shaped structure or a stranded like a structure, like elastic, like collagen, you know, a lot of those tissues that have fibers, all right? You learn about, these are called fibrous protein. Versus there is a globular protein. Globular protein, they're kind of like, you know, spherical and so on. You know? So, you know, they could have a weird shape, but there might be a spherical, there might be like, you know, tertiary or quaternary and things in that nature. A good example of that would be antibodies, hormones, enzymes, they're all protein. You can find a lot of different protein in your body too. Underneath your skin, what's shaping the skin? Collagen is a protein. Your hair is a protein. Your nail is a protein. Hemoglobin in your red blood cells is a protein. All right. Enzymes that helps you to break down the food is protein. We can see examples of protein everywhere. But one thing that you really, really need to understand is that the shape of the protein determines the function. The shape of the protein is extremely important. All right, extremely important. All right. So as you know, something about what is happening today is like, you know, these coronavirus, they have these spikes, and these spikes are a specific shape that they could attach to our cells so they could get in. All right. They work beautifully for this virus. All right. If they don't have these spikes, they can't get in. They won't be able to harm us. All right. But it's kind of like a landing gear. Have you seen like rovers or those things that they send to the other planet? They land gear, boom, they come into and sit on the planet. It's kind of like that. All right. So the shape is really important for what they do. That is the function. If you mess up with the shape of the Lego pieces, you're going to have the same problem. They're not going to fit with one another. You know, if you smash a couple of them with hammer, they're not going to fit with one another anymore. They become useless. Same thing in here. Now, protein can get denatured. In other words, when they are no longer folded the right way, they may not react the same way. They may not have the function the same way. All right. So many factors can affect that. One of those factors is a pH. When you change the acidity and basicity, just put the Lego pieces in something that is really acidic. It might melt. So no longer you're going to use that piece. It loses its function. All right. Uh, Temperature. If you put maybe Lego pieces in the oven, all right, it will melt. It's not going to have their job anymore. It's not going to stick to anything. All right. After it cools down, it just doesn't do anything. All right. Same thing with these. All right. If you have a functional enzyme, they must have retained their shape. All right. So have you noticed if you have a fever, you don't feel like eating? Even if you want to, you feel like throwing up and you can't eat. Right? A lot of times when you're sick, what happened. Your body temperature is up. That's heat. All right. The body temperature is up. That's heat. That's going to affect a lot of enzymes. And a lot of enzymes help us to break down the food. And you won't get that. And that's what is happening. All right. During heat, they can break apart, denature. You lose the structure. And unfortunately, they lose their function. No longer they can do their job. All right. So can other things affect the shape? Yes, it can. All right. Salt concentration can change the shape as well. All right. So temperature, salt concentration, pH, a lot of things are important in retaining the shape. If you mess up with the environment, a lot of things. All right. Now, we're going to talk a little bit about the enzymes, folks, and wrap this lecture up. The enzymes happen to be catalysts. They speed up the reaction. Enzyme usually they might have a cofactor to activate them. Enzymes maybe they're always very efficient. They are very specific. What that means is kind of like a specific key. All right, you can't just open up any lock. It's a specific key goes to a specific lock. All right. Usually ends, not all the time, with ASE, like, for example, lipase, you might have heard about. If not, you could probably guess what it does. That's right. It breaks down or helps to break down lipids. What do you think protease might do? Protease breaks down the protein. All right. Amylase breaks down the carbohydrates. And you can see nuclease breaks down the nucleic acid, DNA and RNA. So these enzymes are really useful because our food contains all those four macromolecules, and using these enzymes that happen to be in our digestive system helps us to break things down. All right, so we could get the energy that we need. By the way, you first need to break things down so you could absorb them. From then, it goes into the blood most of the time, and these substances, or smaller substances, they can get distributed through the cell. All right, so you need to break things down. All right, enzymes lower the activation energy. What does that mean? Let's take a look. Activation energy is the energy barrier, is the barrier that they need to overcome. Would be right here. This is activation energy. If we want to roll a ball or a marble, or let's say, you have a bicycle and this is a hilltop, you need to overcome this barrier in order to get to the other side. The other side, let's say, is a product. What you start off with is called reactant or substrate. So we start with the substrate, we end up with the product. But in the course, there is an energy barrier. Well, this is without the enzyme. With the enzyme, the energy of activation, you could see, is lower. Take a look in here. It's lower than this one. Let's call it the A, let's call it a B. Right now, you're lowering, using the enzyme, you're lowering the activation energy. So obviously, you could get to your destination quicker. All right, you get to the product quicker. You don't need to go all the way in the top. All right, so that's called energy of activation. So enzyme lowers the energy of activation. Enzymes are not part of the product. Enzymes are not part of the product. All right, enzymes bind with substrate. So let's say this is the enzyme, and this is our substrate. This is called the S. This is called the E for enzyme. Substrate, they can bind in here. Boom. Now it formed the substrate enzyme substrate complex. All right. They're forming a complex now. Now, sometimes they are fit with one another, induce fit formation, and then after that, it breaks down. So after you break down, all right, this enzyme now broke down this product that is releasing. No longer this product can be fit in here. So now enzymes can actually go and get more substrate to the product. So what is happening? You're ending up with this. All right, this is your reactant substrate. This is your product. Enzyme just helped out in the middle. All right. Again, this enzyme shape is extremely important. All right. Here is another enzyme that instead of breaking things is actually forming things. So here you have a structure that where the substrate binds to is called the active site. This would be this structure right here. all right? So amino acid in this case bind to them, all right? And the enzymes are kind of like uh, fitting, substrate fits into the enzyme. This is called enzyme substrate complex, all right? And then what will happen? In this case, you're making a bond. Uh, it looks like the water is departing. We call this dehydration, and you're making a bigger molecule. This bigger molecule no longer it has a new bond formation is occurring. So this is your maybe one amino acid. This is another amino acid. This is two amino acids now that are joined together by the peptide bonds. So peptide bonds can formulate because the two amino acids are near one another. So boom, they can form. And now you're getting another, this enzyme again to do the same thing, get more reactant and goes. So the example that I gave you previously was basically when you are breaking things. And this example that I just told you is when you are making things. Either way, enzyme can lower the energy of activation and do the things that they do. Now, let me go over a little bit of application, make it fun for you, and then we go to the nucleic acid. All right. So if we mess up with the active site, earlier I told you that the enzyme has an active site right here. This is where the substrate binds. Okay. But if you introduce to heat, now you might have something like that. All right. Where is this substrate going to bind? There is no active site in here because the active site have been altered. Nothing is going to happen. All right. So when you get a fever, that's what happens. You don't feel like eating. All right. But why do we get the fever to begin with when the heat is rising in our body? Of course, negative feedback is going to lower it eventually, but this heat is necessary. What is it doing? Well, let's say you have a bacterial infection. Bacteria can multiply every 20 minutes. Some bacteria, like E. coli, they multiply every 20 minutes. You get more and more and more bacteria, right? So bacteria uses enzyme to multiply. Bacteria uses enzyme to double up their DNA. Bacteria uses enzyme to, put in the amino acids together because their outer wall has certain type of a protein in it, and so on. The heat is going to prevent the bacteria from multiplying because the protein no longer being able to have the same shape and form, and that's why, the fever works. In addition to that, I don't know if you remember last time you had a sore throat, all right? Uh, People sometimes they drink orange juice, they usually gargle maybe with hot water, again, heat, orange juice, they take a lot of citrics, uh, material, citrus fruits, etc., which is again pH. Whenever you have a low pH, your throat feels good now because again you're preventing them from multiplying. All right. Uh, some people they take a warm water, eat, as well as salt. So salt concentration was the next one. All right, and therefore you are again creating conditions for the protein to have a different shape. So as a result of that, enzymes are being proteins, they're not going to work properly. And this would help because you wanted to eliminate all these bacteria multiplying and so on. So again, there are many, many different applications, but I'm just giving you a few of them so you can think beyond uh, and relate it to something in life, for example. All right. Uh, when you sneeze, they used to tell you, "Oh, God bless you," this and that. Now, if you sneeze, everybody look at you funny, like you have coronavirus or something, or some kind of a deadly disease, and they don't like, and they don't. You're not gonna get that much blessing anymore, I guess. But I hope things will change. Anyways, uh, a lot of times when you marinate your meat, you cook it in a high heat to break the bacteria. You apply orange juice or you know what you call it, lemon, spices like creates lower pH. You add salt and pepper and other things that increases the salt, right? So all of that, again, when you marinate the meat, it will take or last longer too, all right? Very interesting. So, uh, going over the enzymes, there are few things that you could think about the enzyme. Now, here is the enzyme, here is the substrate. But what if you have another molecule that might look like a substrate? Like this part, it looks like this part right here. It's like the same curvature. And this part might fit in here. But this is not our substrate. Remember, substrate is the reactant. You want to get it to the product. For example, our product was, cut this in half, for instance, huh? All right. But if you have another molecule, let's say binding in here and blocking in here, all right, now the substrate has nowhere to bind. And as a result of that, you're not going to get that much product. These are called competitive inhibitor. Competitive inhibitor, they compete for the active site, all right? So the more competitive inhibitor you will have, the less product you will have. So for example, you have 10 of these, but you have one of these. For obviously, there's more probability for these to attach to the enzyme. So your reaction rate is not going to be as fast. However, the more substrate you would have, and the more enzyme you would have, the concentration you have, then you will get more. So the more competitive inhibitor you have, if you have more of this, then what happens? Lower the reaction rate and lower product. All right. The less you have a competitive inhibitor, the more product you will have. Opposite, obviously. All right. So it's called competitive because they're competing. Inhibitor, it inhibits because it prevents the substrate to bind. All right. In this case, our enzyme is not changing shape, but it's blocked. All right. It's blocked. Okay. Now, another scenario, this would be the last scenario that I wanted to talk about, is some enzyme, say this is the enzyme again. This is the active site. And this right here is where the substrate binds. All right. This is my enzyme. And let's say you have a molecule, all right, that can bind another area right here. So if it binds in here, a little bit after some time, it binded in here. But take a look, as it binded, it changed the shape of the active site now. So what happens? The substrate cannot bind in here anymore. Why not? Because it cannot fit in here anymore. This caused this shape alteration. This is called non-competitive inhibitor. Non-competitive inhibitor, again, they do not compete for the active site, but they compete for the other sites. Sometimes it's called allostatic site. But don't worry too much about that. Right now, you need to know that the more non-competitive inhibitor you will have, again, same thing, the lesser reaction you would get, the lesser product you would get, because the substrate is no longer binding to the enzyme. All right. How do we know what condition to use? All right. What pH to use? Is all the enzyme works in the same pH? No. The enzyme in your stomach works under very low pH. The enzyme in your small intestine operates in a maybe neutral pH. All right. So they all have a different pH. So how do we know? Well, you have to run an experiment. Here's is your reaction rate. And if you wanted to do it under different pH, you could have different pH. Say pH, you know, 2, 4, 6, 8, 10, 12. You can only go up to 14. And when you do, let's say you're adding the enzyme and the substrate under 2, pH of 2, so this would be pH scale, all right? You might see something like this, watch. It looks like our reaction rate is the highest, and right here is the highest reaction rate. So if you come back down, it looks like maybe in this case, 7 would be the best one for this reaction. But if you have another reaction, you know, because not all the substrates are the same, you might get something like that. Now, in this case, you could see clearly that pH 2 would be ideal for a different reaction. Maybe this is the enzyme that works in our stomach. So you can see and figure out what is the ideal pH for that particular reaction if you do it under different pH. Similarly, you could do it under different temperature and find out which one works best. Similarly, you could do the same thing with the salt concentration, etc. All right. So it all depends. Uh, Interestingly enough, if we have a beaker, let's just say hypothetically, let's say this is a solvent that we carry our reaction, and let's say that you have 2 enzymes. You add 1 substrate, and let's say it takes 1 minute for the substrate to turn into a product that takes 1 minute if you use this enzyme. All right. So if you have 1 substrate, this substrate, maybe I should draw it smaller, is going to go in here, and that would take 1 minute. Boom. In 1 minute, you have a product. But if you have 2 substrate, all right, 2 substrate binds, you have 2 enzymes, so it's still you could accommodate that. Again, that would take 1 minute as well. So in other words, it's going to be faster in this case because you have a substrate, but you also have the enzymes. So now it took 1 minute, but you made double amount of product. All right. But what if you put in 4 substrate now? Will you get, faster reaction rate again? No, why not? Because again, that would take 1 minute to do this 2 and 1 minute to do that 2. So it's 2 minutes. All right. So if you keep on increasing the substrate, you're not going to see increase in reaction rate and product. All right. So for that, it plateaus. Let's look at another scenario. In this case, you have a set number of substrate. Let's say you have 10. But this time you're adding the enzyme. So if you're adding the enzyme in there, it takes 1 minute, all right, for each one to do this. So there are 10 of these, it would take 10 minutes, and then completely you're making a product that you need to. But if you're adding two enzymes, now it would take 5 minutes, if you can see. All right. So anytime you're adding, like, let's say you're adding 4, 5, 6, 7, your reaction rate keeps going higher and higher and higher. All right. Because of the fact that, the more enzyme you will have, all of a sudden you could get all of these substrate and turning into a product quicker. All right. With the difference in here, the enzymes are busy. They're busy working. So even if you have more substrate, all right, you cannot expect the keep reaction rate to go higher and higher and higher. So it's kind of like plateaus because, they're busy. You have to wait until they do this too, and then it recycles and goes back and it attaches to more substrate, and then again you're turning it into the product. So that is as far as I wanted to talk about regarding the three macromolecules. We discussed the protein, we discussed the lipids, we discussed the carbohydrates, two important reactions of hydrolysis and dehydration was covered. So make sure you understand that. We went over the function of the enzyme and the structure of the protein in addition as well. All right. We also looked at the structure of the amino acids. All right. So let me go ahead and stop the recording at this point in time. And